Okay, first thing about test 3, confidence intervals, interpretation. There are some questions on the test that is going to ask you find the true statement. Only one of them is true. There are some questions that mark all is true. So this is one of the conditions that mark all. There are 2 interpretations of confidence intervals, and both of them are correct. So here is the situation. We're going to construct the confidence intervals for the proportion of females who's going to pursue STEM degrees or who are already pursuing STEM degrees. And we ended up with this confidence interval, 48% and 67%. What can we say about this interval if we have a confidence level with the 95%? So this is a generic one. I believe all of you will join me on that as yes. We are 95% confident that the true indicates that this interval is about the population proportion, or we can use word all or total. These are all indicators of the interval is about the population. The females who are pursuing STEM degrees in Wake Tech is between 48% and 67%. That's a generic one. Here's another one though. There is a 95% chance that this interval is one of the intervals that will contain the true proportion, which means that this interval is about the population of females pursuing STEM degrees. I would say yes for this one. I remember we talked in class, chance might not be the appropriate word, but for the sake of through, I would say go for it. A better word that I would prefer instead of 95% chance, 95% probability, but take it as yes. So check. There is 2 good, correct interpretations of confidence intervals. Talking about confidence intervals, any questions, raise your hand. If not, I'm moving. And you can ask a question, please. Just because it's recording, I can stop it. All right, majority. That's another concept about confidence intervals. So we would like to determine the proportion of females, again, who are trying to pursue STEM degrees or planning to pursue STEM degrees. And then we had 200 females in our sample, and 53% of them says, yes, we are going to pursue STEM degrees. And we created the confidence interval. So look, question is not asking you to do anything at this point with the 90%. And this is our interval. Based on this interval, can we say that majority of the female students either plan to pursue or pursue STEM degrees? No. Just because we do have 53% here does not qualify it for the majority. We need to look at the interval here. And in that interval, yes, one end of the interval is greater than 50%. It's 58.8%. However, the lower limit of that interval is below 50%. There's still a chance, there's still a possibility that not majority of the female students at Wake Tech might want to pursue or might be pursuing STEM degrees. So if we are talking about a confidence interval, lower limit of the confidence interval and upper limit of the confidence interval, both ends should have a number greater than 50%. If we want to say that majority. Okay. I'm moving. Finding a critical value. So what is this critical value? It is coming from 9.1 and 9.2 power points in confidence intervals. We find critical values for props, or we might be finding critical values for means. So what is the difference between them? We're going to look at that. So if you're finding a critical value for a prop, here's an example. For instance, what is Z alpha over 2 for 95%? What does that mean? So it means that we are having 95% here in the middle. That's our confidence level. And then in both ends are 5% as a sum. So it means that each little tail will be 5% over 2 and 5% over 2. Well, our Z alpha over 2 is a value here, lower end or an upper. So that's what we want there. So what we're saying, if we have this area, which that area turns out to be 95% plus 0.025, because 0.05 over 2 is 0.025, then it is going to be 0.975. What is this value here? That's what we wonder. We're talking about critical value for a proportion here. Then Z alpha over 2 in generic formula is norm dot inverse area or probability, if you want to call it, 0, 1. While here in our area, norm dot inverse is 0.975 and 0, 1, and then we end up with 1.96. Well, I mean, for 95% confidence interval, you don't need to do any of this. But the reason I instructed you here, what if we talk about an 83%? Then what you're going to do? Okay, what you will be doing, let's say 84%. That's an even number for confidence interval. So it means that we're having 84 in the middle. It means that we're going to have 8.5% here, 8% here, and 8% there. So if I want to figure out what's the Z alpha over 2 here, then I'm going to write down Z alpha over 2, norm dot inverse. This area is going to be 92%. 0, 1. Okay. Whatever that value is, that's how you find it. Well, this is for proportions, critical value. We might need to find the critical values for means for confidence intervals. Then remember, confidence interval for means or hypothesis testing for means deal with t distribution. Well, the critical value in t distribution is found like that. Okay, alpha here represent 1 minus confidence level. So if we are talking about confidence level of 95%, then alpha will be 1 minus 0.95, alpha will be 0.05. Okay, so I'm going to pull it up there. Critical values for means is T alpha over 2 will be equal to T inverse 2T alpha and the degrees of freedom. Well, what is different between these two? Here, as I'm finding the z critical values in proportions, we don't need to know the sample size. We'll get the formula, green highlighted. Let's do this, green highlighted. We don't need to know the sample size. However, if you're finding a critical values for means, running a t-test, then we got to know the sample size. Why? Because we have degrees of freedom. Degrees of freedom serves for n-1. Let's think about this example here, 84%. I need to give you one more piece of information. If I'm preparing a confidence interval with 84% with a sample size of 20, I need to provide that information to you for you to be able to find the critical value if you're dealing with means. Then that will be T alpha over 2, T inverse 2T. Alpha will be 1 minus confidence interval, which is confidence level. Alpha will be 16%, and degrees of freedom will be 19. And whatever you get from the Excel, that's just a number. Cool. Try to see side by side what's different to find a critical value between props, proportions, means. We don't even have to tell you find the T critical value. We can really talk about very general for this case. If I'm telling you I want to construct a confidence interval for sample size 20 with a confidence level of T 84%, find the critical value, you got to decide which one you're dealing with. Because we are expected to know that critical values for means will be obviously T critical value. All right, moving on with the confidence interval. There's a different way to find confidence interval. There's a problem on lab manual, I believe, at the very beginning of finding confidence intervals for means. Page 70, problem number 1 in lab manual is very similar to that. So here's a question. In Halloween, with 90% confidence, we can say that the average number of candies our neighborhood kids collected were between 122 and 178. What's the margin of error? Okay, what are they telling us? So our kids collected candies. We created this confidence interval. Then what would be the margin of error? Quite frankly, this number even not needed. Now you can think that, oh my God, there's no n. There's nothing else. How are we going to figure out? They're not asking us to construct a confidence interval. They're giving us the interval. So I need you to remember this. How are we ending up there? We're ending up there. We do have a sample mean, and we're adding a margin of error to that sample mean. We do have a sample mean, and we're subtracting a margin of error, that sample mean. So when we add, we're ending up with 178. When we subtract, we're ending up with 122. That's the case. Well, from there on, it's not statistics. It's 2x2 solving systems. All right. So if you add these two equations side by side, we are going to end up with 300. Then the mean will be 150. And then I'm going to use it in one of the equations here. So 150 plus margin of error was 178. All right, that margin of error will be 28. Done. So there's less statistics here, but more thinking of statistics there, and just a little bit of math. Okay, this was a problem on page 70, lab manual, number 1, also very similar to this. All right. I mean, you can plug it in on the second equation if you want. This one there. So x bar, we ended up with 150 minus margin of error was 122. And then you can pull out the margin of error from here. It's just solving equations. Right. Then you are going to end up with 150 minus 122, 28 will be equal to margin of error. All right. The last thing that I want to talk about, confidence interval, is a confidence interval we're going to figure out from the proportion. Confidence intervals for proportions with the data. So under week 15, there's a unit 3 test review material, and there's an item there. So if you download that Excel file, we will be talking about that Excel file and the problem there. Okay. So the problem is, who is going to pursue STEM degrees? Construct a 90% confidence interval for the proportion of females in STEM degrees or trying to pursue STEM degrees in wave tech. So there are 64 students in our sample. And I highlighted the female, because our interest is about the females here. So when I count them, I ended up with, okay, we do have 40 females out of 64. So then I figure out my p-hat. That will be equal to 40 divided by 64. Then q-hat will be okay, just a second. Am I sharing my screen? That I need to check. Oh, yep. Now let's talk about it again. All right. So in that document, we are looking at 64 sample size. Out of that 64, 40 of them are females. And then we are calculating our p-hat. Remember, x over n. We have 40 females out of 64, so that is giving us our p-hat. Q-hat will be 1 minus p-hat here. I feel like I'm losing my, no. Yeah. Okay. Every time I move my Excel, I'm losing the screen. I guess, all right, now it's okay. So once we figure out what's p-hat and q-hat, we are going to go ahead and find the margin of error here. Okay. And margin of error is going to be z alpha over 2 times p-hat q-hat over n in square root. Let me take this guy here. There is an easier way of doing these things after the Excel. Oh. Now let's get this guy. Let's get it all here. Yeah. Now I can talk about it. Okay. So from your Excel, once you get P hat and Q hat, what's left to figure out margin of error? What is margin of error? It is Z alpha over 2 times P hat times Q hat over N in square roots. Okay, the problem was about confidence intervals 90%. So because we have confidence, all right. All right, let's keep this guy here. All right, let's go back here and keep the screen there. Yep. So then confidence level was 90%. So Z alpha over 2 will be 1. All right. It's a mess up. So many things are happening at the same time. 1.645, and then when you place all those figures, we're going to end up with the margin of error equals to that number here. Okay. So this problem was different. Why? Because we figure out P hat from the data by counting. Once you get that, all you need to do, plug in to this formula here. Okay, this was about the review for confidence intervals that I needed to pull your attention. Obviously, there are many other things, but these are the ones that crucial that you may want to visit again. Hypothesis testing. We never accept H null. We never reject H alternatives. Okay? That's what we need to remember. Example. Say that we set up our hypothesis with null, proportion of female students who would like to do STEM degrees at Wake Tech is less than or equal to 35%. Well, I claim that it is greater than 35%. Then I found a sample which gives me P hat 38%. Well, my sample is in line with my claim. Well, that's the way it should be, right? Okay, now I'm trying to do, it's going to right. Nope. Screen going, but maybe my claim is in line with my sample, or my sample should be in line with my claim. I'll take it back. Otherwise, we don't run the hypothesis testing. And then we find some p-value. We figured out that is less than or equal to alpha. We have a decision. We're rejecting H null. All right, what does that mean? It means that our sample, my sample with the 38%, supports the claim. Without running the test, I wouldn't be able to say that. I run the test, I check this, I look at the p-value. Is this one of the rare samples there? We might have a couple of samples greater than 35%, but that doesn't make the whole decision for the whole Wake Tech. We need to come up either with a confidence interval or a hypothesis testing while we run the test, and then we can say data supports the claim. if we're rejecting H null. There is also another way of saying it. We can say that the data indicate that the proportion of female students who would like to pursue STEM degrees is significantly higher than 35%, the person is likely correct. We can also say that, right? So just because we know the generic meanings, we are 95% confident, yada, yada, yada. We have enough evidence to support the claim, yada, yada, yada. There are other ways of saying it, and that will be correct. Okay? So let's have a look to a second example. This time, same claim, I have my 38% sample, but that I'm ending up with a p-value, let's say 15%. Well, it is greater than any alpha, whichever alpha you choose, either 1% or 5%, and I'm going to end up with failing to reject H null. Well, what does that mean? There might be too much of variability in the sampling distribution. It means that there are samples like that, and it is just a variation of the sampling distribution. It is against the status quo, which is 35%. But although I have a test statistic, I have a 38% value, I have a statistics that is going to support my claim, consistent with the alternative hypothesis, it is not significant. Okay? That's another way of saying it. All right, I'm going to stop this recording.